Something happened on the moon, and almost nobody knows the full story. In the official mission summary released to the public, Artemis 3 was described as a landmark achievement, a triumphant return of human beings to the lunar surface for the first time in over 50 years. The astronauts collected samples, tested new equipment, validated life support systems, and planted a flag. That's the version most people read. That's the version that made the headlines. And that version is not wrong, exactly. It just isn't complete. Because buried underneath the press releases and the carefully worded mission updates, something else was happening at the lunar South Pole. Something that didn't make it into the summary documents. Something that caused quiet meetings behind closed doors. Something that changed the way a lot of very serious scientists think about what the moon actually is. If you want to understand what that thing is, you first have to understand why the South Pole matters so much. And I mean really understand it. Not the two-sentence version they give you in a news article, but the deep version. The version that explains why every major space agency on the planet has been trying to get there for years, and why Artemis 3 landing at Shackleton Crater was one of the most consequential decisions in modern space exploration history. So stick with me here, because this goes places you probably didn't expect. And if you're new here, hit subscribe before we get into it. We do this kind of deep dive regularly, and you don't want to miss what's coming next. Let's start from the beginning. For most of human history, the moon was assumed to be bone dry. A dead, airless rock, with no water, no weather, no geology worth speaking of, and certainly no surprises. The Apollo missions seemed to confirm this. The rocks that astronauts brought back were analyzed extensively and initially appeared to contain almost no water whatsoever. Scientists concluded that the moon formed from a violent collision between the early Earth and a Mars-sized body, and that the extreme heat of that event had vaporized any water that might have existed. The moon was dry, case closed. Except the case was not closed. In 2009, a NASA mission called L-Cross was deliberately crashed into the moon's surface near the South Pole. The idea was to kick up a plume of debris from a permanently shadowed crater and analyze what was inside. The result shocked a lot of people. Water ice. Not trace amounts, not ambiguous readings. Significant quantities of water ice, sitting in the shadows, preserved for potentially billions of years. This changed everything. And here's why the South Pole specifically is where all of this gets interesting. The moon's axial tilt is only about 1.5 degrees. That's almost perfectly upright compared to the plane of the solar system. What that means in practice is that there are craters near the lunar poles, where the geometry of the moon's tilt means sunlight never reaches the floor. Not in a season. Not ever. These are called permanently shadowed regions. And inside them, temperatures can drop to around -250 degrees Celsius. That's colder than the surface of Pluto. Cold enough that water ice deposited there over billions of years, from comets, from asteroids, from the early solar system itself, can sit completely undisturbed, frozen in darkness, for geological timescales we can barely comprehend. Shackleton Crater at the South Pole is one of those places. It's about 21 kilometers across and nearly 4 kilometers deep. The rim of the crater receives almost continuous sunlight, which makes it a perfect location for solar power generation. But the floor sits in permanent darkness. And inside that darkness, radar and spectroscopy data from multiple missions suggested there was ice. A lot of it. When Artemis 3 was being designed, the South Pole wasn't just a destination. It was a target that had been chosen with extraordinary precision after years of orbital reconnaissance by missions like the Lunar Reconnaissance Orbiter. Scientists thought they had a very good picture of what the astronauts would find. They thought they understood the terrain. They thought they understood the composition of the regolith. They thought they had run every simulation, every model, every projection needed to prepare for what was down there. They were not entirely right. Now, before we go any further, I want to be clear about something. I'm not about to tell you that astronauts found alien structures, or that there were underground cities, or anything like that. Those are not the kinds of surprises that keep real scientists awake at night. The things that actually unsettle serious researchers are subtler than that. And in many ways, they're more disturbing. Because they don't fit into the models we've been building for decades. And when something doesn't fit the model, it means the model is wrong. And if the model is wrong, everything built on top of that model has to be re-examined. What Artemis 3 encountered at the lunar South Pole was 3 separate anomalies. And I want to walk through each of them carefully, because each one individually is fascinating, but together they suggest something that nobody has publicly stated in clear terms yet. The first anomaly was the ice, not the presence of ice. Everyone expected ice. The anomaly was the nature of the ice. What the astronauts found when they began collecting samples from the shadowed regions near Shackleton was not what the models predicted. The ice was layered, not randomly scattered through the regolith the way most scientists expected, but arranged in distinct horizontal strata, clean layers separated by thin bands of darker material, like sedimentary rock here on Earth, like something that had been deposited in repeated, distinct events over time rather than gradually accumulated. Now, this sounds like a detail. It sounds like something that only matters to geologists and planetary scientists. But think about what it implies. If the ice was deposited gradually, uniformly, over billions of years, you would expect a more or less homogeneous distribution throughout the regolith. You might find more concentration in certain areas due to local topography and temperature gradients, but you wouldn't expect clean layers. You wouldn't expect stratigraphy. For you to get layered ice deposits, you need episodic events, discrete delivery events, separated by periods of relative quiet, and the spacing and thickness of those layers, which the Artemis 3 crew documented meticulously during their EVAs, suggests a pattern, a rhythm almost. Delivery events that appear to coincide, when the data is back-calculated, with periods of elevated cometary impact flux in the inner solar system. What that means is that the Moon's south pole has been acting like a geological archive, a frozen record of cometary bombardment, going back potentially billions of years. The ice isn't just water. It's a historical document, and reading it carefully might tell us things about the early solar system that we cannot learn any other way. That's the thing about the Moon that gets overlooked. People think of it as a simple object, an inert rock. But because it has no plate tectonics, no significant atmosphere, no liquid water on its surface, it doesn't erase its own history the way Earth does. The Moon remembers. It holds on to things. And the South Pole, in that permanent cold darkness, preserves those things at a level of fidelity that is almost unimaginable. The layering data from Artemis 3 is now being analyzed by teams at multiple institutions, and the early findings are significant enough that several researchers have quietly described it as potentially the most important geological dataset collected on another world since the Apollo core samples. That's not a statement you make lightly, and it hasn't been made loudly, publicly, in a press release. It's being said in conference rooms and over email threads, and in preliminary papers that haven't cleared peer review yet. That was the first anomaly. Now let me tell you about the second one, the magnetic field readings. This is where things start getting strange in a way that even non-scientists can appreciate. The Moon, broadly speaking, doesn't have a global magnetic field. Earth has one. It's generated by the movement of liquid iron in our planet's outer core, spinning around the solid inner core. This is called a geodynamo. It's what makes compasses work, and what protects us from solar wind. The Moon's interior is not active in the same way. It cooled down, its core solidified, the geodynamo stopped, and so the Moon doesn't have a planetary-scale magnetic field the way Earth does. But here's the thing. Some parts of the lunar surface have local magnetic anomalies, patches where the ancient rock is magnetized, left over from when the Moon's interior was still active billions of years ago. These magnetic anomalies have been mapped from orbit. Scientists know they exist. They're interesting, but they're not surprising. They're just remnants of an old magnetic field, preserved in the crust. What Artemis 3's instrumentation detected was different. During the traverses conducted near the southwest rim of Shackleton crater, the crew's portable magnetometer readings began behaving in a way that didn't match the orbital maps. There were regions where the local magnetic field was significantly stronger than predicted. Not just slightly off from the models, substantially stronger. And the distribution of these anomalies wasn't consistent with the patterns you'd expect from ancient magnetized crust. When you map ancient magnetic anomalies, they tend to follow the broad contours of the underlying geology. They correlate with large impact structures, with ancient volcanic features, with the grain of the ancient crust. They make geological sense once you look at the context. The anomalies detected by the Artemis 3 crew near Shackleton did not obviously make that kind of sense. Their locations and intensities were not clearly correlated with the surface features or the subsurface structure that the ground-penetrating radar suggested was present. Now, there are several possible explanations for this, and I want to be fair to the science here. It's possible that there are subsurface iron-rich deposits whose presence wasn't predicted by the orbital data. It's possible that the geometry of nearby impact events created localized magnetization patterns that are more complex than the models captured. It's even possible that there's something about the structure of the ice deposits that affects how magnetic measurements behave in that environment, a kind of interference effect that nobody had accounted for. All of those explanations are on the table. None of them have been definitively confirmed. And what the mission team is not saying publicly, but what has been discussed internally, is that none of those standard explanations cleanly account for what was measured. The anomalies are real, they're documented, and they don't fit neatly into the existing framework. Why does this matter beyond being a scientific curiosity? Because magnetic anomalies of this type, particularly if they turn out to be associated with subsurface metallic concentrations, have significant implications for future lunar construction. Any permanent base at the South Pole will need to account for the local electromagnetic environment. Electronic systems, navigation equipment, life support monitoring systems, all of them are sensitive to unexpected magnetic interference. And if the South Pole's magnetic environment is more complex and more variable than the models suggested, that's not just an interesting scientific puzzle. It's an engineering problem that has to be solved before humans live there. But that's not even the most unexpected finding. The third anomaly is the one that has people talking in quiet voices, the one that showed up in the data collected during the deepest penetration of the permanently shadowed region on the final EVA. Heat, specifically a localized thermal anomaly, a region of the crater floor that was measurably warmer than the surrounding area. Not dramatically warmer, not glowing, not anything so dramatic as that. But in an environment where temperatures are stable at minus 250 degrees Celsius, a region that measures consistently 20 to 30 degrees warmer than the baseline, and that maintains that temperature differential over the period of observation, is deeply anomalous. The Moon has no significant internal heat source. The radioactive decay that drives geological activity inside Earth and that made the early Moon's interior molten has largely played out over the past several billion years. The Moon is cold, it's thermally dead, and at the South Pole, in permanent shadow, far from any direct solar input, you would expect temperatures to be essentially uniform. The only variations you'd anticipate would be due to differences in thermal conductivity between different materials in the regolith, or perhaps slight heating from cosmic ray interactions with the surface, or the thermal influence of nearby sunlit terrain conducted very slowly through the rock. None of those mechanisms produce a localized warm spot of the kind the instruments found. The thermal anomaly is relatively small, a few hundred meters across at most, based on the ground-level measurements taken on the final traverse before the crew had to return to the ascent vehicle. It's deep on the crater floor, near what appears to be a region of particularly high ice concentration based on the ground-penetrating radar readings. And it is, as far as anyone can determine, still there. It's not a transient event, it's a persistent feature. What could cause it? This is where I want to walk you through the serious scientific thinking, because this is not a simple question, and the answers people are privately considering are genuinely fascinating. The first possibility is tidal heating. The Moon's orbit is not perfectly circular. It's slightly elliptical, and as the Moon moves through that ellipse, the gravitational pull of the Earth flexes the lunar body slightly. This flexing generates heat through friction, the same basic process that makes the subsurface ocean of Jupiter's moon Europa stay liquid despite being so far from the Sun. But here's the problem with this explanation in the context of what Artemis 3 found. Tidal heating on the Moon is extremely small. The numbers don't work to produce the kind of localized thermal anomaly observed. Tidal heating would produce a diffuse, subtle effect spread across the whole Moon, not a concentrated warm region on a crater floor. The second possibility is radioactive decay from an unusually concentrated deposit of radioactive material in the subsurface: uranium, thorium, potassium. These elements exist in the lunar crust, and their decay does generate heat. There are regions of the moon, the ones geologists call the Procellarum creep terrain, where these heat-producing elements are concentrated enough to have maintained elevated temperatures over geological time. But the South Pole is not a creep terrain, it's compositionally different, and again, the localization of the anomaly is the challenge. You'd need a very high concentration of radioactive material in a very specific spot to explain what was measured. The third possibility is the one that nobody wants to say out loud in public because it sounds too speculative, too far out, too much like the beginning of a science fiction story. But I'm going to say it, because the scientists who are thinking about this are thinking about it, and pretending they're not doesn't serve anyone. The third possibility is that there is an active geological process occurring in this region that we don't understand. Something in the subsurface that is generating heat through a mechanism that our current models of the moon's interior don't predict. It wouldn't be volcanic in the traditional sense. We have no evidence of recent volcanism at the South Pole, but the moon's geological history is not fully understood. We know that volcanic activity continued much longer than initially expected, with some evidence suggesting eruptions as recent as 100 million years ago in certain regions. 100 million years sounds like a long time, but in geological terms it's practically yesterday. Could there be deeply buried heat sources, pockets of material that are radioactively anomalous, or ancient magmatic intrusions that have retained heat in ways that the models don't capture? Could there be a chemical process, a reaction between subsurface materials and the ice deposits, that is releasing energy? Could there be something happening at the interface between the ice and the silicate rock that produces heat as a byproduct? None of these questions have been answered yet, and the honest truth is that answering them requires more data than Artemis 3 was able to collect. The thermal anomaly was identified late in the mission. There wasn't time to deploy additional instrumentation. The crew was already near the limit of their consumables for the EVA. They documented what they could, collected a small number of samples from the edge of the anomalous region, and returned to the lander. Those samples are currently being analyzed, and the results of that analysis are going to be watched very carefully by a lot of very smart people. Now I want to zoom out for a moment and give you the context that explains why these three anomalies, the layered ice, the magnetic irregularities, and the thermal anomaly, are particularly significant when you consider them together. Because in science, anomalies happen. Data doesn't always match models. Instruments malfunction. Local conditions produce unexpected readings that turn out to have mundane explanations once you look more carefully. This is normal. Science is full of surprises that turned out to be noise. But what makes the Artemis 3 situation different is the coherence. These three anomalies aren't random. They're all concentrated in the same general region. The area of strongest magnetic anomaly overlaps spatially with the area of highest ice concentration, which is in the same general vicinity as the thermal anomaly. That spatial clustering is not something you'd expect from unrelated random noise. When three separate, independently measured anomalies cluster in the same location, that clustering is itself information. It suggests a common cause. It suggests that there's something about that specific region of the crater floor that is fundamentally different from what the models predicted. Something structural. Something that is affecting multiple measurable properties simultaneously. And here's what that means for our understanding of the lunar South Pole, and by extension, for our understanding of what it will take to establish a permanent human presence there. For years, the South Pole has been marketed as the ideal location for a future lunar base. The near-continuous sunlight on the rim provides power. The ice in the permanently shadowed regions provides water, rocket fuel, and radiation shielding. The terrain is challenging but navigable. The location has been presented as essentially solved. We know where we're going. We know what we'll find. We just need to build the vehicles and go. The Artemis 3 data suggests that our confidence in that picture may have been premature. Not wrong, not dangerous in an obvious way, but premature. We had incomplete knowledge, and the way in which it was incomplete is informative. Because the things we were wrong about, the complexity of the ice stratigraphy, the character of the local magnetic environment, the presence of a thermal anomaly, these are exactly the kinds of things that will matter enormously when you're trying to build and operate a permanent station on that surface. A thermal anomaly, whatever its cause, introduces uncertainty into how the ground will behave. Will it be stable? Will ice in its vicinity sublimate unpredictably if the heat source fluctuates? What does it mean for drilling operations, for foundation stability, for the thermal management systems of any structure built nearby? You need to know. And right now, we don't know. The magnetic complexity affects navigation and communications in ways that require detailed local mapping before you can design reliable systems. The layered ice structure means that drilling for water resources requires a different approach than expected, and the potential scientific value of that stratigraphy means you don't want to just blast through it carelessly. None of these are showstoppers, but they are complications. Real, substantive complications that require real, substantive engineering responses. And the fact that they weren't in the public mission summary isn't necessarily because someone decided to hide them. Mission summaries are written for a specific purpose. They communicate accomplishments. They highlight milestones. They're designed to be readable by a broad audience. The nuanced, uncertain, preliminary findings that come from data that is still being processed don't fit easily into that format. But that doesn't mean the findings don't matter. And it doesn't mean people shouldn't know about them. Let me tell you a bit more about the specific details of the EVAs, because the operational reality of what the crew experienced adds a layer of context that you don't get from reading instrument data. The terrain near the permanent shadow line at Shackleton is unlike anything in the Apollo record. The Apollo missions all landed in the equatorial regions of the Moon, in relatively flat mare terrain, ancient volcanic plains that offered safe, predictable surfaces. The South Pole rim is mountainous by lunar standards. Slopes, boulders, terrain that shifts from well-illuminated sunlit ridges to the absolute darkness of the crater interior within meters. The transition zone, the boundary between sunlight and permanent shadow, is one of the most extreme environmental gradients anywhere in the solar system. Crossing that line with a spacesuit was something that had been practiced extensively in simulations. But simulations, no matter how sophisticated, cannot fully replicate the psychological and physiological reality of stepping from brilliant sunlit rock into total darkness while wearing life support equipment that keeps you alive and communicating with a crew module sitting on the rim above you. The suits used for Artemis 3 were equipped with advanced lighting and thermal management systems. They were designed for exactly this environment, but the crews who trained for Apollo described how the Moon constantly surprised them with small, unexpected details that simulations had missed. The same appears to have been true at the South Pole. The regolith in the shadowed region behaves differently from the sunlit surface material. In the extreme cold, the uppermost layer is more compacted, more brittle. Footfalls behave differently. Tools interact with the surface differently. The first crew member to step fully into the permanent shadow spent several minutes just characterizing the ground behavior, communicating back to the surface operations team, adjusting the planned sampling approach based on what they were actually encountering, rather than what the models had suggested they would find. This adaptive response is a fundamental part of human exploration, and it's something robotic missions simply cannot do at the same level. A rover can collect data from wherever it goes, but a human being can look at what's in front of them, recognize that it's different from what they expected, reason about why it's different, and change their approach on the spot in ways that might capture information a robotic system would have missed entirely because nobody had thought to program it to look for that particular thing. The thermal anomaly, for example, was first noticed not by the instrumentation, but by one of the crew members observing that the surface texture in a particular area appeared different from the surrounding terrain, smoother, slightly different in color under the suit lights. The observation was flagged, the portable thermal imager was deployed to check the area, and that's when the anomalous readings were recorded. A robotic mission, following a pre-planned traverse route, might have passed right through that region collecting its standard suite of measurements and never specifically flagged the anomaly because nobody would have been there to notice the visual difference first. This is one of the arguments for human exploration that is genuinely compelling and that doesn't always get articulated well in the public discussion. It's not just about inspiration, or flags and footprints, or national prestige. It's about the irreplaceable value of having a reasoning, adapting, observing human mind on the surface of another world. The moon is full of things we didn't predict, and the best tool for finding things you didn't predict is a human being with good training and the freedom to follow their curiosity. Now, let's talk about what comes next. Because the Artemis 3 data is not going to sit on a shelf. It's going to drive decisions about future missions, about the design of the lunar gateway, about the architecture of whatever permanent presence humanity eventually establishes at the South Pole. And the specific character of the anomalies found there is going to shape those decisions in ways that are already being discussed. The thermal anomaly is the most urgent. It needs to be characterized properly, and that means returning to the site with dedicated instrumentation. A network of surface-deployed thermal sensors left in place over multiple lunar days could establish whether the anomaly is stable, variable, or evolving. Understanding its behavior over time is essential before any major construction decisions are made for that region. And the science case for understanding its origin is independently compelling, because whatever is causing it is telling us something about the moon's interior that we currently don't understand. The ice stratigraphy needs to be sampled more completely and at greater depth. The samples collected by Artemis 3 come from the uppermost layers. To read the full historical record that appears to be preserved there, you need to drill deeper, much deeper. The kind of coring operation that could reveal a comprehensive record of cometary bombardment over billions of years requires equipment that wasn't part of the Artemis 3 payload. It's part of what the designers of future missions are already thinking about. The magnetic anomaly mapping needs to be expanded. The portable magnetometer measurements taken during the EVAs provide point measurements along specific traverses. To understand the full geometry of the anomalous zones, you need a dense network of measurements across a broader area. That could be done with a network of small surface-deployed magnetometers or with a low-flying drone that doesn't yet exist in operational form for the lunar environment, but is being developed. All of this points to the same conclusion. Artemis 3 wasn't the end of the story of the lunar South Pole. It was the beginning of a much more interesting chapter, and the things it found that weren't in the public summary are precisely the things that will drive the story of lunar exploration for the next 20 years. There's something worth saying here about the nature of exploration more broadly, because I think it applies to this situation in an interesting way. One of the persistent misconceptions about scientific exploration is that its primary function is to confirm what we expect to find. That expeditions are sent out to validate existing theories and check boxes on a predetermined list. That's not how it works. That's not how it has ever worked. The history of exploration is a history of surprise, of arriving somewhere with a map and finding that the map was wrong, of expecting one thing and finding another, and of the one thing you found turning out to be more interesting than the thing you were looking for. The south pole of the moon is not the predictable, well-characterized site that some of the pre-mission communications suggested. It is stranger and more complex and more scientifically rich than the models captured, and that's a good thing, not a problem, a feature. The universe doesn't owe us the right to predict it perfectly with limited data. Every time reality deviates from our predictions, that's the universe offering us a window into something we don't yet understand. The layered ice is telling us about the history of cometary bombardment and the structure of the early solar system. The magnetic anomalies are telling us about the complexity of the lunar interior and the limits of orbital remote sensing. The thermal anomaly is telling us about a process occurring in the moon's subsurface that our current models don't account for. Together, they're telling us that we need to go back, with better instruments, with more time, with the specific questions these findings have generated. And that's exactly what exploration is supposed to do. Not provide final answers, reveal better questions. Let me take you back to the moment when the crew was preparing to leave the surface. The final EVA was complete. The samples were secured. The crew was running through the ascent checklist. And somewhere on a hard drive inside the lander's data storage system was a collection of files that the analysts back on Earth were already eagerly waiting for. Raw instrument data, unprocessed magnetometer readings, thermal imager frames, ground-penetrating radar transects, sample logs, the full record of what two human beings had observed and measured in one of the most extreme and least understood environments in the solar system. When that data started coming down, there were people in rooms who had dedicated years of their lives to understanding the lunar South Pole, and they were seeing things in the preliminary readouts that they needed to look at again. Things that made them sit forward in their chairs and say, quietly, "That doesn't match what I expected." And that sentence, spoken quietly in a data analysis room, is often the most important sentence in all of science, because it's the beginning of a new understanding. The public mission summary talked about historic firsts, about the extraordinary accomplishment of returning humans to the moon, about the samples collected and the systems tested and the milestones achieved. All of that is true, and all of that matters enormously, but the parts that weren't in the summary are the parts that are going to matter most in the long run. The anomalies, the surprises, the things that didn't fit. Because those are the things that are going to send us back. And when we go back, we'll be going with sharper instruments and better questions, and the specific knowledge that this region of the moon holds secrets that we have only just begun to understand. The permanently shadowed craters of the lunar South Pole are not just iceboxes waiting to be mined. They are archives, records of deep time, written in ice and magnetism and heat, and the ancient structure of stone that has not moved or changed for billions of years. Reading those archives completely is going to take generations of work. Artemis 3 opened the first page, and what was written there was not what anyone expected. Now zoom out even further. Think about the broader context in which all of this is happening. There are multiple nations currently developing lunar South Pole missions. China's Chang'e program has explicit goals in this region. India's Chandrayaan missions have been gathering data. The European Space Agency, JAXA in Japan, and several commercial entities are all developing capabilities oriented toward the same target. The lunar South Pole is the most strategically and scientifically valuable piece of real estate in the near solar system right now, and everyone serious about space exploration knows it. When Artemis 3's data is fully analyzed and the findings are published, they're going to land in a scientific community that is already intensely focused on this region. And findings like the ones we've been discussing, findings that suggest the South Pole is more complex, more geologically active in subtle ways, more scientifically rich than our models captured, are going to reshape the planning of every mission that follows. Every rover, every lander, every crewed visit is going to be designed with this new information factored in. That's how exploration advances, not in a straight line toward a predetermined destination, but in a zigzag, responsive, iterative process in which each mission's findings redirect the next. Artemis 3 just delivered a significant redirection, and the missions that follow will be better for it. There's one more dimension to this that I want to discuss before we wrap up, and it's the one that I think has the deepest long-term implications. Not just for lunar exploration, but for our understanding of where Earth's water came from, where Earth's building blocks for life came from, and what the early solar system actually looked like. The layered ice at Shackleton Crater, if it is indeed a record of episodic cometary bombardment, is a dataset of extraordinary value for answering some of the oldest and most fundamental questions in planetary science. We know that comets carry water. We know that they carry organic compounds, carbon-bearing molecules, amino acids, the precursor materials for biochemistry. We know from isotopic analysis of meteorites and comets that there were periods of elevated bombardment in the early solar system, events like the late heavy bombardment that may have delivered a significant fraction of Earth's oceans and possibly some of the raw chemical ingredients for life. But the details of that delivery, the timing, the frequency, the specific character of the material that was delivered, are poorly constrained. We've been trying to reconstruct the bombardment history of the inner solar system from the crater record preserved on the moon's surface, on Mars, on Mercury. But that surface record is imprecise. Craters overlap, they erode, the timeline gets blurry. A stratigraphic record of ice deposition, if it can be dated accurately and correlated with specific cometary populations, is a different kind of evidence entirely. It's not a count of impact craters. It's the actual material that was delivered, layer by layer, in a frozen archive that has been sitting untouched in the dark for billions of years. Reading that archive carefully could give us a timeline of cometary activity in the inner solar system more precise than anything we currently have. And from that timeline, we might be able to say more definitively when water arrived on Earth, and whether the same delivery events that watered Earth also delivered the organic chemistry that eventually became us. That's not a small claim. That's potentially one of the most significant scientific findings in history, sitting in a frozen crater at the bottom of the moon, waiting to be extracted and read. Artemis 3 found the first pages of that archive, and what it found suggests the archive is real, it's extensive, and it's more orderly than anyone dared hope. The layer structure means it can be read, means there's signal in it, not just noise. And that signal might connect directly to the oldest and most fundamental questions about our own origins. This is why what Artemis 3 found matters so much more than a mission summary can capture. Because a mission summary is necessarily written about what the mission set out to do, about objectives met, milestones achieved, systems validated. It's about the plan. But the most important things in exploration are always the deviations from the plan, the unexpected readings, the puzzling observations, the anomalies that make you go back to the drawing board. The moon has been sitting out there for 4.5 billion years. It has been watching the solar system evolve. It has been recording things in its rocks and in its ice, and in the complex magnetic memory of its ancient interior. And we have only just arrived at the most interesting part of it with instruments sensitive enough to start reading what it has recorded. What we found wasn't what we expected. It never is. And that, if you'll allow me to say it plainly, is what makes this the most exciting time in the history of lunar exploration. Not the flags, not the firsts, not the triumphant press releases. Those matter. But what matters more, what will matter for 100 years, is that we went somewhere we thought we understood and found out we were wrong in specific, informative, scientifically profound ways. We went to the south pole of the moon and found that the ice is older and more structured than we knew, that the magnetic field is more complex than our maps suggested, that there is warmth in a place that should be the coldest, darkest, stillest location in the near solar system. The moon is not what we thought it was, and now we have to go back and find out what it really is. That process has already begun. The data is being analyzed, the papers are being written, the missions are being designed, and somewhere on the rim of Shackleton Crater, in the near-continuous sunlight where solar panels will one day power a research station, in the permanent shadow below where the ice archive waits frozen in the dark, in the patch of crater floor that is, inexplicably, measurably warmer than everything around it, the moon is waiting to tell us the rest of the story. And we are finally learning how to listen.